So in today's lesson, we're going to talk about 1.6 photoelectron spectroscopy, specifically PES data, or what they call PES data. And so we're going to touch upon this idea of how to do these problems and what exactly is PES. So the shell model and the periodic table really highlight a couple of things. The first one has to do with this idea called first ionization energy, which is the amount of energy needed to remove an electron from its outer shell. And so the first row of the periodic table has two elements, hydrogen and helium, and it only holds two electrons, so these don't want to be removed. So they're going to have a very high amount of energy, which is about 2,300, 400 kilojoules per mole. So for every mole of helium or hydrogen, you're going to need 2,000 and change of energy. That's a lot. And so if you take a look at the second row, this one has 8 elements, and they go from lithium all the way to neon, and these can hold up to 8 electrons maximum, and so on. And so as you can see from here, the ionization energy really kind of starts dropping as you're increasing in rows. But as you're taking a look at why that's the case, we need to understand what that looks like. So the first row of the periodic table has two electrons. We talked about it. They have a full shell right here with helium. Second row, we have neon, and we're looking at 8, and so on. And as you're increasing these orbitals, level 3 can actually hold 18 electrons max. And so, as you're adding in these suborbitals, electrons can fit in to these a lot better. Now, we talked about how there's an inner core electrons and there's outer core or valence shells, not outer core. And the valence electrons are really the ones that bind or attract to another element. So sodium's element right here, this electron will love to bind to another element, maybe, for example, chlorine, and it would donate that. And it really has to do with the fact that this lone electron right here likes to be given off so that it can actually become more stable. And so PES really is an extension of that idea. It's called photoelectron spectroscopy, or PES. And pretty much what they do in these experiments is that they have high energy photons that will remove electrons from any shell, not just the outer shell. So we already know that valence electrons bind to another element, but really what happens with these photons is that they can actually hit anything. And so what happens is that, you shoot these photons out, and what they do is that they get ejected. These electrons get ejected. There are some electrons that go a little slower and some go a little faster, and as they get ejected, they kind of start attracting themselves to this positive side. And that kinetic energy of electrons is determined based off how fast these electrons are moving. So some electrons, as I mentioned, have very high energy, so they're going to maybe shoot on this side. Some of the lower ones are going to be in there. And what they do is they also record the frequency of the photons. So in other words, the wavelength times that amount. And usually there's a correlation. In other words, the higher that frequency of energy, the higher that kinetic energy. And that ionization energy is then used to calculate that amount. So those values you see earlier, the ionization values, those are calculated from photoelectron spectroscopy. And they don't just make it out of thin air. Scientists have to find a way to measure how hard it takes to remove these electrons away from their shells using these photons. Now, normally what you would do is you would beam X-rays or UV light, and these photons would just shoot through and knock these electrons out of the way. So a photoelectron spectra is basically like a map. What it does is that it shows you how many electrons you have relative and how much energy it takes to remove them out. And so depending on the amount of energy that you're actually removing these electrons out, it kind of tells you where they're primarily located. And so if you take a look at these, you can kind of see that we have different levels and areas for this element. So for example, boron has 3 areas of ionization, and normally it reads from highest to lowest versus the other way, which is lowest to highest. Boron has 19.3, 1.36, and 0.80. Beryllium has 11.5 and 0.9. And so as you can see from here, it actually ends up being that it can actually tell you how many electrons are in the shell. And so what ends up happening here is that based off of that spectra, you can tell we already know hydrogen has only one electron, and in order to do that ionization energy, it will actually require quite a bit to pluck out that energy right there, which is 1.31 megajoules per mole. And if you take a look at carbon, carbon here has three areas or three shells in which they have ejected electrons. One at 28.6, one at 1.72, one at 1.09. And so if you take a look at these, if you take a look at carbon, its placement, carbon is in row 2 of the periodic table, which means that it's going to end with the 2 subshell. So carbon has 6 electrons, 1s2, 2s2, and then your 2p would be here, right? And the reason why these values are so high is because at the 2s level, it takes a lot of energy to remove carbon. Now, you take a look at nitrogen, look at the periodic table for nitrogen. Nitrogen has nitrogen has 7 electrons, and so obviously you would have, again, your 2s, your 1s2, 2s, your 2s2, and then your 2p, whatever it is, 2p, 2p246, 2p4, that would actually have this specific one. So your p orbital is going to be right here. And so basically these represent orbitals. And what would happen here is that if you were to remove this is how much energy it would take. And so by taking a look at this actually tells you how many orbitals you actually have. So usually the way we do this is you take a look at subshells. So 1s contains a maximum of 2 electrons, 2 contains 2s and 2p with a maximum of 6. So you have 8 electrons on the 2 shell, and then your 3 goes up to d10, which means you got 2, 6, 10. That's a total of 18 total electrons. And so here's the energy in megajoules obtained from PES. And PES basically, again, I was telling you earlier, is how much energy it takes to remove these electrons from all its different shells. As you can see, for sodium actually takes 104. 104 is actually a lot of energy for sodium. So that means that sodium's first electrons, its initial electrons, are going to be extremely difficult to remove. The 2s right here, it's a little easier to remove, but not as much, 2p and 3s. And so as you can see from here, every single orbital that you have, as you're getting further and further away from the nucleus, you can actually, it takes less energy to remove these. And that's the reason why we have these PES spectroscopies to determine those ionization energies. And so after learning about PES data, do you see a need to refine the shell model? And so the question here is there a way to kind of address some of the issues with a shell model? And the answer is the shell model actually has all energy electrons within a given shell are at the same energy. It basically assumes that. So if I have a 1s, they all have energy levels. So the PES data, however, shows us that there are 2 subshells in 2, and there's 3 in 3. And so basically what we need to do is account for the fact that the 3 subshell actually has 3 sublevels, the S, the P, and the D, while the N has the S and the P. And so these are actually at different energy levels. And so is there another model that we can use that could explain this a little better? And the answer is called, yes, the quantum mechanical model. Quantum mechanical model actually is it's a much more better way of showing that data than, for example, your shell, because of the fact that you have subshells that have different energy levels. And that's going to basically bring us to our PES questions.